Sarthak, can you hear me? Hello?
Yes, sir.
Can you see the screen?
Yes, sir.
Hello?
Yes, sir.
Okay, let me start. I will start next of 11:55. Let's see. It is working. So this is tau, a topological compact space. So you take its compact Hausdorff space. So the you have this metric space. This is submetric. Actually, it comes from this norm. So that for this space, Ascoli-Angelo theorem tells you characterize compact subsets in CXT. So this is one problem always, to give a topological space, particularly a metric space and nonlinear space, to characterize compact subsets. And now another problem happens that even in YAL, if you have a topological space, the question actually query. Don't confuse with that. Suppose in YAL you have is what are the nice if it is separable, it will be still nicer. But if you have nice dense subsets, you should understand that then means basically suppose A is a dense subset. That means each element of this, each X can be, let me explain that, approximated by the elements of A. So let me more specific in that. So X tau is dense in X means its definition a bar equal to X. Okay, so even if it is not first countable or metrizable or metric space, and that still you see that given X belongs to X, so X belongs to X, that means X belongs to a bar. So there exists a net X lambda in A converging to this. Now if you have this metric space and A is dense, then instead of this net you can have a sequence. There exists a sequence Xn in A such that Xn goes to X. The approximation means yes, here's net, here the sequence converging. That is the idea of the approximation. Approximation in terms of the elements. Elements of A. So that's why the now if you have nice dense subset, if it is that means nice, most often it means that you really have a lot of information on A. You know that. Not necessarily countable. If it is countable, it will be separable. That's a good thing. But even if it is not separable, if you have a lot of information on A, that means it's a nice thing. If you do not have much information on A, then it may not be a good dense set. So that means the nice meaning is that you on A you have about A you have a lot of information. Then each element of X you can approximate like this or this, depending on whether it is a first countable space or not. So you can do that. So look, in Ascoli-Arjela theorem, that now look, Ascoli-Arjela theorem we had. Again, I'm coming back to that. Here you have, don't confuse it, it's a compact space. Compact, so you have CXT. This is a complete metric space. Here, since it is compact, every continuous function is bounded. Complete metric space. And we have got characterization of compact subsets. That is Ascoli algebra theorem. But now we are interested in that nice dense subsets in CXT. Suppose you have this thing, suppose this A, because it's a collection of functions that is vectored. If you have this, then what it means, already I told you approximation. So this is a metric space. This is a metric space. So that any element F, given F, belongs to Cx, there exists Fn, a sequence in A such that Fn goes to F with respect to the metric T. Okay. So that means F can be approximated by these Fn. Now these Fn, so if A is nice something, if you can, nice means always you have a lot of information on A and they behave well, basically, informally. So if you have this, that means this is. So you can have, that means any element of X, Cx can be obtained in terms of A. That is called approximation theorem. Now, what are we talking about? Stone-Weierstrass approximation theorem. Okay. So that, well, just let me explain that. Of course, you have this where X is a compact space. You can take Hausdorff space if you want. Now the thing is that you may ask first of all why two names up there? Why two names up there? Stone was a mathematician of the last century, whereas Weierstrass was before that, 19th century basically. And Stone was a mathematician of basically 20th century. And Weierstrass basically 19th century. Of course, his work overflowed in 20th century. But why two names up there? Now when we'll see that in some result you have 2, 3 mathematicians. Then so probably somebody did a special case proved, and then somebody came to generalize that. Then both the names will come. Look, Weierstrass, there is why it is known as that. That is the corollary in the node I have put corollary 2.3. Okay. That any real valued compact subset actually to an interval. Suppose you have this interval, that means you take C of this. Okay, all continuous real valued functions on this. Okay, so particularly you can take this. It's a compact subset. This. So for any compact subset of that it can be done. But basically Weierstrass did this or this here. What he did, he said any continuous function can be approximated by a sequence of polynomials. The uniform limit. Uniform limit means with respect to metric T. I'm just explaining that that is Weierstrass theorem. That before that, that means he said if you have F here, these two are basically same. If you have a continuous real valued function on the closed interval 0, 1, then given there is just a sequence of, here I should tell you something about polynomial functions. such that Pn, of course, you are considering this metric. That is boisterous result. And Stone, the word we want to do it, generalized to this. Okay. So that's why it's called Stone boisterous approximation. But boisterous result was this. Okay. Right. And Stone did that. We'll prove this. But here, let me tell you that something that here. But before I go to anything, I want to say I am not using polynomial, I am using polynomial function. Look, I think since you have done algebra, there is a big difference, polynomial and polynomial function. Look, usually we write a polynomial like this. Over some field, whatever you take ring. Here, when you guys do it over R or C, this is actually, you say X is indeterminate variable. Here, you are not taking P as polynomial. Here, Px is a polynomial function because if you plug X, you can define like here, whatever, like here from this. So you plug any value of X, basically pick up any value of X, then you get this. Here, this is a polynomial function. Polynomial function means a function of the polynomial form. That is called the polynomial function. But what actually polynomial means? In algebra, we did polynomial over a ring R. Then, okay, let me ask you something. I do not think you have been taught that. That here R, we take this so-called. But here, what is the ring? Suppose just a ring. So you said this is the ring of polynomials. Ring of over R. The ring here, not the real line, it's the ring. But what is it's a notation. So what is the meaning of X here? Have you thought of this? That is no meaning actually.
Finite.
Huh? What was saying? R is an arbitrary ring, and this you are saying ring of polynomials. Then what is finitely? That means you are usually take something like this. After that, everything is 0. But this n will change. Okay, and this comes from this. That means basically sequence with finitely sequences over R with finitely many non-zero elements. That's the thing. The X कहाँ से आता है? What is the meaning of X here? Then forget about this. Then what is the meaning of X? Yes, we are saying the finitely many non-zero entries. So that here over R, we are getting this. R is a ring. N will change. N may change. That means basically it is sequences. Okay, sequence, you know that basically this is coming. So you are taking sequences with condition and only finitely many non-zero entries. This 0 means 0 of R. That means if you take a sequence here, okay, suppose n here, you are getting, call it an, and here there exists m depending on n belongs to n such that n equal to 0 for all n greater than n. Okay, this gives you, and this you can prove it will be a ring. Component wise addition, component wise multiplication, component that is called the Cauchy's multiplication. You know that, and in fact it will be an algebra also. So that's the ring, and then it is also can have by scalar multiplication, depends on the field if you take, but that's a different thing. Over ring, it will be it's a ring. Okay, and usually we write this x right now doesn't have any meaning. This is just a notation. Okay, this is the polynomial. You addition you have component wise, and multiplication is, suppose you have two rings, two elements. Not necessarily same thing. Then their multiplication will be like Ci, okay, and where Ci is summation ak b I minus k 1 to I. I think I have written correct, I minus k. Okay, so if k equal to 1, k is 0, actually you're starting 0 to I. A0 bi. Similarly, okay, a1 b I minus 1. So this is the definition of the product you define. यहाँ पे x नहीं है, so it doesn't make sense. Okay, right? I'm just talking about polynomial, not polynomial function. But here, of course, you do not have any polynomial, but x makes sense. Now look, usually while defining polynomials, we take with 1. Why we take that? It makes a lot of difference in characterizing polynomials. And that if you have this, then you call, let me tell you that, this polynomial, right? Everything 0. This is the polynomial. Okay, what? This you call x. And then any such polynomial you can write this way. Look here. So you're getting a so-called well-known polynomial form. Here x means this, and the product with itself, x square with itself, that's the product, that is called the Cauchy product. That I said that how to define. So these are, so this is polynomial defined product. And this you can think of the product or think of scalar multiplication. And also you know that what to do that. An means constant polynomial और भी 0 आएगा. That way you can think of that. Usually we think of that way. So this is another polynomial. Okay, so this you can write. So the so-called standard form of the polynomial. But unless, look, this is not defined unless you have this one. This one is the identity of multiplicative identity of the ring. Okay, so that this. Now let me tell you that. So something you did in algebra, when you have the polynomials on that, you substitute it. Substitution. Suppose now we have a polynomial over R. So R with 1. And so that you have this something polynomial. Okay. But when you have an element in B, suppose, then you have written this. Look, this X I already told you what is the meaning of that. Then you have something substituted and work with this. Particularly, you have division algorithm. But this is an element in R. Okay, right? This makes sense. But often from here you came with this to have some result from here. How you came from here? Here it is in Rx and it is in R. They are different things, though it is a polynomial ring over R. Okay, so you manipulated the things here like this. Why it is justified? These are two different things. Something you are working here, then you're substituting, you are getting this. It is when you substitute development, basically you are using this as a polynomial function. But it is not a function. That I told you what is the polynomial means here. It is actually meaning x, and you are taking the product of polynomials and then sum of the polynomials. Okay, and this is a different thing. Okay. This is R. Okay, so just think about it. But in case of R, now look, so that if you take this ring, I will have this. This is the collection of all polynomials over R. R itself is a field, so it particularly is a ring. But polynomial function, look, this is the thing. Here, about Stone-Weierstrass theorem, you will always find polynomial functions, not polynomial only. Though people sometimes loosely speak of polynomial, but it should be talked about, we should talk about polynomial function. Look, polynomial function means a function of the polynomial form. So don't confuse with a polynomial. That means, what do you have? That means if I have R, suppose I have element in R, and I can have this function. Okay. Look, this x belongs to R. You are plugging defined. This x is not that x, the previous polynomial thing. Okay. So I said fx, you write this. Look here, says this x is a variable. Here it makes sense x is a variable. It's like for function you define domain. You take any subset also like this. Doesn't matter. Then x will be restricted to this. So this makes sense because this will be another real number. So this is a function. So this is more precisely you should call it polynomial function, not polynomial. Polynomial function. So Stone-Weierstrass theorem, we talk about polynomial function. Don't confuse with the polynomial, though sometimes loosely we talk about polynomials. Okay, so think about what I told you the previous thing, substitution. So previous thing I should tell you that here you need to have something called substitution ring homomorphism. You need this, otherwise this is not justified. I don't know which book you followed, but here is a good book by Hungerford, Thomas Hungerford. Indian edition is available. Name of the book is Algebra. There you can find. Here you need substitution ring homomorphism. But what I emphasize to say that polynomial and polynomial functions, they're different. Okay. And you should, in the context of polynomial, you should know the meaning of x. But here you do not have a problem. Here x is behaved like a detail that is very so-called variable for a function. Okay. Now here, Weierstrass is a in any real world continuous function and a compact subset. Actually, written on closed boundary interval is the uniform limit. Uniform limit means in the metric space CXD you are working with that uniform metric of a sequence of polynomial. I have written polynomial functions. Polynomial functions. Now, just to make the casual mentioning, this stone, there are two stones, famous stones in mathematics. Here you see MH stone. This is actually Marshall. Okay. You have the Alitrans working so they have in a footnote here. Okay, so that yeah, I think footnote had, which is the footnote Alitrans working so. Footnote is here. Marshall, this is Harvey. Stone is an American mathematician. In page 88, you will find in the footnote. Okay, and his lifespan was this. Said he contributed to Boolean algebra, topology, the theory of function and function analysis. Function analysis, there is one famous theorem called Banach-Stone's theorem. So Stone had contribution that Banach-Stone, that is a function analysis. And theory of functions. Of course, theory of functions means this. Here you have Stone-Weierstrass theorem and Boolean algebra. That you can see that what is Boolean algebra. Boolean algebra has applications in computer science, also in major theory and that. Okay. Now about this stone, another stone I have not talked about this. He died in 1989. You should go to that. I won't tell you that. Look, where did he die? Actually, he was visiting India that time. I think he was in Institute of Mathematical Sciences, Chennai. He died in Chennai, the old Madras. Okay, right? So this is American mathematicians. But here, another mathematicians that you'll find Arthur. This is spelling of Arthur. This H stone. H stone. He is a British mathematician. He was a British mathematician. And I don't know, I would like to just mention one time that called stone-check compactification. Stone-check compactification. Compactification of a topological space. If it is not compact, then how to get a space in which a compact space in which it will be dense. That is the idea of stone-check compactification. This stone is this stone. Okay, so that much I am telling you that if you get, you'll always hear of two stones in. You should read mathematics seriously, but you should know which stone they're mentioning. Okay. Now, so this you can go to the net, you can see that. Well, now I talked about two stones. Okay. This is Marshall Harvey stone. This is Arthur stone, H stone. This H I do not remember that. But one mathematician joked one is a Marshall, other one is a field Marshall. Okay, because both are great people in mathematics. Now, about Stone-Weierstrass approximation theorem, I told you that. So that let me tell you something now, very seriously. Stone-Weierstrass. I will give you a problem in measure from Stone-Weierstrass. It's not something like I'm teaching and I won't ask you in the exam. I will ask you in the exam. The students who are not attending, they will find out. It will be more difficult than minor. Stone-Bois stress approximation theorem. So I am picking up first Ali Pranti's book. Okay. I am looking first. I want to go by results and this thing. Okay. In this section, we shall present some conditions under which a linear subspace of Cx with X compact is linear subspace, is dense in Cx with respect to the uniform matrix, dense. The main result of this set of this sort is known as the Stone-Bois approximation theorem. It is a classical result. So then separating functions and that, okay. So that in order to this Cx, we're taking X compact space. Continue. Okay. Now he is putting the condition that is on the separation of points by functions. Why he is not talking about Hausdorff? That actually he is assuming there is Hausdorff, stronger than Hausdorff. Separation of points of X by functions, in Cx. That means given a pair of points, distinct points, given X and Y, there exists F. He is doing for a subset of that, but in Yan, separation of points by function such that Fx not equal to Fy. So it's a real valued function, so that if you take 2 epsilon equal to this, then X belongs to this F inverse. And Y belongs to look, it is a continuous function, it is open set, so this is open. Similarly, this is also open. And because of this 2 epsilon, these two open sets are disjoint. So it will be automatically Hausdorff. Okay. Separation of functions by this. Linear is taking by functions and a subset of that. But this is still fine, no problem. Ultimately, it is a subset of this. So it will be automatically Hausdorff. It is called actually, such a thing is called functionally Hausdorff. You are separating by functions that is stronger than Hausdorff space. Okay. So basically he is taking compact Hausdorff space, but stronger than that. So that is a separation of points. Any to distinct points you get a function, then it is called that. Okay. And I said L, if you take L, non-empty set, and that L separates the language that I am explaining the language. Okay, that you need to understand first. So suppose L is this. Then the definition we say that L separates X, points of X. Its meaning is that given xy belongs to X with X not equal to Y. That's a pair of distinct points. There exists L. L is a subset of this. I was explaining first over Cx. Now I am putting more conditions. The F belongs to L, that such that Fx not equal to Fy. Okay, right? Okay, fine. You have got that. So this is the definition of the separation of points. Okay, right. Now, coming to point. Here, he is apparently giving two versions, lattice version and algebra version. A famous stone versus. And in order to prove that is the last theorem of this section. That is, this lattice version is theorem 11.3 and algebra version is theorem 11.5. Okay. Now lattice version matlab kya hai? That means if you have FG, that means you have not only a dense set, look, that means a late, late XP compact, all these things and that, and L separates functions and points, and this is very important on that. L. Look, remember that here is saying this. Let me first explain that. What is the lattice version so called? He's saying L. L is a subset of Cx, because L is non-empty. L is lattice in the function space. Remember that I have given you the definition of function space. Function space, first of all, it is a vector space such that it is a lattice as well. That means basically partially ordered vector space. That partial order is standard order. Comparison of two functions in that. Remember that. If fx equal to gx for all x belongs to this. So partially ordered vector space where any two elements have supremum and infimum. That is called the lattice. That is the property of the lattice. If any two elements have supremum and infimum, that means, look here, L, the function space first of all, then L separates points of x. That I already explained. Okay, with the function space. That means, what does it mean? It means if G belongs to L implies okay. The third thing is saying the constant function. This is has to be constant function belongs to L. Here constant function 1 means 1x equal to 1. This one is a function, this one is the scalar of R. Okay, 1 belongs to L. If you have the separate points, we have this. Of course, L is a function space, L is a vector space there. Okay, so you are assuming L is a vector space, vector subspace, linear subspace. Okay, then I have this. L is dense. Look, why I said talked about nice dense subsets. Already I'm assuming many nice things about it. So that's why it's a nice dense sets. Okay. And he's calling, they are calling it lattice version because of this. Okay. And 11.5 algebra version. Okay. So that, but point is that most of the books on the authors, they only talk about algebra version. And in the proof of the algebra, you have the lattice version. Now I'm coming to the point. I'm taking this few minutes rest that I'm coming back. Is horse there? Hello? I'm looking for horse. Horse is there? Hello? What happened? Hello?
Yes, sir.
कहाँ है हॉर्स को दो हेलो हॉर्स हेलो
यस सर।
ये तुम खराब क्यों किया एग्जाम में
तो सेकंड क्वेश्चन में दिक्कत हो गई थी।
दिक्कत हो गई है आई सॉ यू दैट यू आर ओनली overturning pages and that your kid that means you are not well prepared huh? You know in the US the rule is that if you overturn your pages more than 5 times you are not going to do well in the exam. You think it is open book, open access, everything, so that you don't need to prepare. Make sure that you do well in the major exam. You don't need to ask me recommendation, but if you go abroad to PhD and if you want recommendation, I want to do well in topology. Otherwise, I won't write reco for you. समझ गया?
यस सर।
हाँ. If you are interested in pure mathematics, I can help you to get there in a good school, good university. Okay. Now, come to this point. First of all, I am spending a lot of time not only for exam. I'm trying to teach you some analysis also. Now look here. So this is the lattice version, and they separated lattice version, algebra version. Authors usually prove the algebra version. That is the famous, well-known Stone-Weierstrass theorem. But in this lattice version, that part of the proof it comes inside the proof for algebra version. But here, let me talk about lattice version. The result is not wrong, but their proof is wrong. Let me tell you that explain that you should read that. That means this theorem is correct. That's why I had in my book I had a different proof of that. Okay. But where is the mistake that I want to tell you that. So make sure that you read Ali Francis Barkinson this section very carefully, including the proofs. Proofs are the what they're talking about. They are not difficult. That you can understand. But now look, theorem 11.3. Statement is correct. That is lattice version is there, but their proof. So let me explain where is wrong. While writing my book, then I realized that mistake is there. I was looking at the proof and that. Okay. First of all, look here. Their algorithm is that they have used lemma 11.2. Okay. In order to prove lemma 11.2, they have used this. So lemma 11 is correct. The proof is also correct. Now look at this. The culprit is this. So that look, if you look at the theorem 11.3 that I already explained, lattice version of Stone-Weierstrass theorem, so-called. I already explained that. Remember that. This is the thing. I said this is the lattice version. Okay, right? And if this is wrong, okay, I do not know about the statement that the proof is wrong because I think still it can be proved. But that actually you'll have to see that what proof I have given. So whether that works. So if your proof is wrong, then obviously if you are using this, then it will be wrong also. Okay. Now, so that they are using They are saying lemma 11.2. So they are using. If the proof is wrong, their proof cannot be corrected. Okay. So let me see that what is lemma 11.2 they are saying. Lemma 11.2 they are saying X is a compact Hausdorff space that I told you that Y can't assume that is a compact Hausdorff space. Okay, and L is a function space. That I told you what is the meaning of function space. This is a vector space with the for any pair of elements in L, you have the supremum infimum is also in L. Okay, and like that. So L is a function space 1. The constant function 1 belongs. Here I should tell you that 1 belongs to L. मतलब क्या है? If you take constant function, that is alpha x equal to alpha. For all x belongs to x, where alpha is a real number. Then you see that means alpha. What is the meaning of the 1 actually? That this alpha you can write, not function alpha, you can write alpha scalar multiplication of this. Okay, you can write that. But if 1 is there, it's a function space, particularly vector space. So it will be there. So actually the idea is that all the constant functions are here. That we say just by 1. That will be equivalent if and only of the because 1 itself is constant if and only all constant functions are there. So when L is a function space, then 1 belongs to L is equivalent that all the constant functions are there. That's the idea. That by this statement you ensure that all the constant functions are in there. And now they are saying so you have L function space because that exactly they use so-called lattice version for Stone-Weierstrass theorem. Okay. And of course you have this and L separates points of X. These are the hypotheses. But actually they need the next theorem, lattice version. Then they're saying, then given the function g, given a g belongs to cx, there exists a point and a point, sorry, given a g, a belongs to x and epsilon greater than 0. That means you give me all these things. G belongs to this, A belongs to X, epsilon. Then there exists F belongs to L. Cell. That is the idea of the approximation is coming such that Fa equal to Ga and okay. This is the thing. If you have this, of course, first you are assuming that the hypothesis you have about L, whatever you get in the so-called lattice version of Stone-Weierstrass theorem. Then you have this, giving G belongs to this, that means G you are approximating basically by F. Now look at the proof. Look at the proof. They are assuming in the proof, look, they are using lemma 11.1. Listen to me. Lemma 11.1, the points are distinct. It is clearly written. X and Y are distinct. But in the proof here, he's saying for each X, he's getting a function satisfying that property. That what property? Look, for each X, there exists, is claiming by lemma 11.1. a function that exists by lemma that exists. F belongs to fx. Since is x, so you're calling index. That fx belongs to L such that fx equal to say equal to GA. They are taking the value GA and GX and fx fx and fx x equal to gx. Look, for each x I'm doing it, but then it is fixed. That means he is doing it, but he is doing it what? He is taking two values alpha beta, GA, GX. In lemma 1, 11.1, this is your alpha and beta. Alpha beta need not be distinct, so there is no problem with that. GA and GX. Okay, right? Then he is getting, they are getting this, okay? And of course, that continuous function that you do in the undergraduate analysis that I can explain again that. Okay. And then they are getting compactness here using and there. Problem is here for each x. That means they are doing it for this pair actually. Pair of points, x and a. Okay. If x equal to a, then obviously you can't apply lemma 11.1. Got the point? That is the mistake. I don't know how they made this mistake, which is apparent. If x equal to a, then these are then they can't apply. You can't apply. Well, if you think that if x equal to a, then itself I will take that function fa equal to I will take g. Remember that here it is given g belongs to cx. G did not belongs to L. If G belongs to L, then I have nothing to, I don't need to do anything. So that is the problem. Fa equal to G will work. But problem is that G may not be in L. So this proof is wrong. Okay, got the point. So this proof is wrong. See, you can see that you can try whether you can rectify this proof. Okay, that much I will tell you that when you come to the algebra version, so that their 11.3 proof of 11.3 is wrong. They are using lemma 11.2. Make sure you read 11.2 again. Actually, you should read the proofs because I will give you 3 problems from the exercises here. Unless you are familiar with the proofs, you won't be able to do them. Okay. So that this proof is wrong. So that lattice version I am not going now. Okay. Right. But I want to go straight that what is known as Stone-Weierstrass theorem. Okay. So that I explained to you. Before that, I want to explain to you the algebra. They're talking about algebra version. If you go for some PhD interview somewhere, it's a good place and that. They won't ask, often they don't ask you the proofs of big theorems of that. Often they ask these conceptual things. Look, algebra version. You remember that if you have Cx, algebra version means what? Algebra, first of all, what is algebra? First of all, you have is the vector space, the scalar multiplication, and I put this another so-called product between two vectors. So that with this, I already explained, this is a vector space. And suppose this you have this product. But then you have this, they will have to be, when you have considered this a vector space, they are compatible with each other, scalar multiplication and vector addition. But it has to be compatible with both vector addition and scalar multiplication. Okay, right? So this means that actually it has to be a ring also. Okay, right? And you can see that. That means ring, and what is the multiplication and this means and that. That means you have this thing. Suppose UV plus W. This U, sorry. That means vector addition is compatible with product, and the scalar multiplication with this. That what will mean this? That means with this. It should be like this. That means this product of vectors should be compatible with these two operations also. Then actually it becomes a vector space as well as ring. Okay, then it is called algebra. Okay, right. Now you look that CX. CX, we have all these things. Okay, so CX is actually is an algebra. Okay, right. Now I say don't confuse with this X. Suppose you take a non-linear space. Remember what is the norm? Norm is the generalization of the concept but to have on R this mod function. This is the generalization of the mod. Non-linear space. Suppose you have it. I have given an algebra on that. And I can have normed algebra. We call it normed linear algebra also, but normed algebra is fine. Normed algebra means this becomes an algebra also. Then it's called normed algebra. Now look, Cx, if X is compact, then Cx, this is a normed algebra. Okay. I have not still gone to the proof of that. That I'm coming in that. That probably another class I'll do it. Okay, right. So it's a normed algebra. You can check that. Okay. So your normed linear space, you have another structure algebra, then it's called a normed algebra. And that is the functionality, advanced functionality. It's a non-linear space. If it is complete, then it's called a Banach space. Right. And if you have non-linear algebra at the same time Banach space, then it's called a Banach algebra. Okay. You remember it is a Banach space complete. So it actually it's a Banach algebra for a compact Hausdorff space. Okay. Here your topology and metric is playing a big role interacting with linear structure, vector space structure. Now I am trying to build up the what you need to know about the algebra version. Otherwise, you won't understand the proof. Now, suppose you're starting with a non-linear space. Now, look, suppose Y is a linear subspace of X. But then X has the topology because it's a metric space. Y bar is makes sense. Okay, that means Y is contained. If Y is a linear subspace, then Y bar is also a linear subspace. Here, vector addition, scalar multiplication, the continuous, it makes a big role. Remember that in here you could prove that if xn goes to x, don't confuse with this y, yn goes to y, and alpha n goes to alpha in the scalar field. It implies xn plus yn goes to x plus y, and alpha n xn goes to alpha x. This means the scalar multiplication is continuous. This means vector addition is continuous. Now look, if you apply this, if I take alpha beta belongs to scalar field. Scalar field means either real or complex. Okay. Either real or complex. Okay. So that suppose you take xy belongs to y bar. I'll have to show, you need to show alpha x beta y belongs to y bar. Only then it will be established. Linear space. Closure of a linear space is linear space. Okay. Said algebra version where I want to prove the closure of an algebra, sub algebra is again an algebra. So that here you look, you take xn, so that xn goes to x, yn goes to y. Okay. Then by this, alpha xn goes to alpha x. You're taking alpha n equal to all alpha. And beta yn goes to beta y. So alpha xn plus beta yn by this goes to, but xn yn coming from y. Xn yn, they are in y. They are in y. So this is, since y is a linear space, this is in y. So I am getting a sequence of elements coming from y converging to this. That means this belongs to y bar, which exactly needed to show. That means y bar is a linear subspace. Right. Now similarly, you can try to show that if now you see that what I want to say that suppose this is a non-linear algebra. Suppose this is all an algebra. That is, it's called sub-algebra. Linear subspace, and we don't say that linear sub-algebra, we just say sub-algebra. Or you can say linear sub-algebra. Linear sub-algebra. Then y bar will be also an algebra. The sub-algebra of that. Same way you can prove, the way I proved. Okay, right. Here you are having the product of the vectors. Okay, you should see that. Basically, you need to prove that if, look, if alpha n goes to, sorry, not like the product we're taking, so that suppose you have xn goes to x, yn goes to y, then you'll have to show that xn, yn goes to xy. Look, since you are assuming it's a sub-algebra, so it will belong here, y. So it will be becoming a sequence. Basically, I have using the characterization of closed subset in both directions. Hello, you are listening to me? Horse?
Yes, sir.
Listen to me. So that, so we are using the characterization of closed sets, closure points. In a metric space, it is sequential characterization of closure points, the both way. So you are getting, if you have algebra, then it will be there in y. So it will come, so it will be in y bar. So that if you have sub-algebra, okay. If you have sub-algebra, then it will be, closure will be also a sub-algebra. Okay. The same way you can prove that. How do you prove this one? Okay, right. Let me see that. You'll have to manipulate the thing in that. That means something like this. You'll have to do this x, y, and x. Okay, non-algebra, you see that you have another properties here. That is, okay, I'm just non-algebra, we need to another thing that norm of xy is this. This will come. In function space, you see x, you have that also. Okay, norm of x, this I forgot to tell you. When non-algebra, you need this thing. Okay, this is condition. Okay, it is in addition to algebra. But anyway, I don't need that here because for Cx I just need an algebra. But here you see, by triangle inequality you will get look here. This goes to 0. This goes to 0. This is a number, just mod x. But this one, you should be careful. Look, yn goes to y. Yn is a convergent sequence, so this is bounded. This is bounded. This you need. This is bounded. Bounded by something like this. So now this goes to 0, this goes to 0, so this goes to 0. So you can prove that. Okay, x1 yn goes to xy. Okay, right. So closure of a sub algebra is again a sub algebra. Okay, and this is also true for Cx. This you need to put the condition for algebra. Now that exactly we have used in the proof. Okay, so that we should do. The difference in a non-linear space, closure of a linear subspace is again a linear subspace. Closure of a sub algebra is again a sub algebra. That is a sub algebra. Okay, right. And here you see that the proof. Look, lemma 2. Now I'm coming to this separation of point lemma 2.1. I want to give the proof of that today, and I just explaining all the concepts under lemma 2.1. Look, this is in my note in my book that they have given that. This is same as Aliprant's lemma 111.4. Okay, right. This lemma 11.4, that proof is correct because it's a standard proof available in the literature. And theorem 11.3 is not available in the literature. They are giving their own thing. Actually, they wanted to have an algorithm of the proof of the algebra version. That's why they split into small results and finally show that their proof looks much shorter than the proof I have given in my book. Okay, so that I want to explain in that. So their idea was that, but in the process they made a mistake. Now look, his lemma 2.1. Okay, this is very vital. This is needed in the proof of that. Theorem 2.2, Stone-Wester approximation theorem. What this thing is? That means here he is saying this. I am considering this metric space. This. Okay. That's the Stone-Wester theorem, the Weierstrass original theorem. That I do not know the proof. I will prove it as a corollary here. But here, this is very vital. This proof is simple, but you should look at the proof. Okay. I'm not going to talk about the proof. You should be able to understand the proof. You should read the proof. I want to talk tomorrow about the proof of theorem 2.2. Okay, right. So that here they are saying that if you take this function, Look, x is positive. So it makes sense. And it is continuous also. Okay. They're saying that there exists a polynomial, they have taken the big P. Polynomial function, that means polynomial function. Okay. Here I am writing P and not x and that. Because if we write function, fx is the value of the function at x. There exists a polynomial function such that Pn converges to this root x, this function in D metric. Okay, right? That they have done. In fact, the proof is constructed. That means they are constructing, and they are constructing by induction, PMI. Okay. That means first they have taken P1 x, P1 is 0 function. That means P1x equal to 0 for all x belongs to 0, 1. Okay, right. And then now look what they're defining. Defining, suppose you have defined up to Pn, then they're defining Pn plus 1 x, defining Pnx plus half look, first of all, x minus a. Since Pn is a polynomial function, its square is also a polynomial function. So it will be a polynomial function. They're taking. So Pn plus 1, if given Pn is a polynomial function, Pn plus 1 is also a polynomial function. Now look here that look, P1x is equal to 0 and Pnx. Now we prove by induction that Pnx is equal to root x. Now look here, first of all, for n equal to 1, the proof is trivial. Assume now that you have this. You have this for all x. This is the induction hypothesis for all x and up to n, 1 to n. Okay, now so that look, it is that now they're proving what? They're proving this is less than x. Okay, this is plus actually. This is minus, sorry. Let me write next page. So that Pn plus 1 x is Pnx. Here it is plus half x minus just going to take put another. Look, Pnx is less than equal to root x. That means Pnx its square is less than x. That means it's a positive. Okay, so Pnx is positive. So this is positive anyway coming. Okay, right. And so that this is this. So we are getting this. And now he's saying that look, Pnx this root x. But x is lying in between 0 and 1. So this is less than 1. Okay, right? So that here you look. Here we have done this thing. But they are doing this. Pn1 plus x equal to Now look, Pnx is less than 1. This is also less than 1. So this is less than 1. So this is positive. Okay. And this is positive. So this whole thing is positive. Okay. This is less than equal to 2. So this is less than equal to 1. So this is positive. And this is positive by hypothesis, induction hypothesis. So whole thing is positive. That means Pns formula also will be this. Okay, right? And you should have this, that is an increasing sequence. That means this. These are all polynomial functions, the continuous functions. Okay, and bounded above by 1. Okay, bounded function. Okay, first of all, look, I want to apply Dini's theorem. So that I want to ensure they converge pointwise. Look, Pn plus 1, it is increasing function and always bounded by this. That means 1. That means for any particular point, if you take this, go for a real sequence. It is going increasing and bounded by 1. So it is bounded above. So that means it will converge to its supremum. That means this converge pointwise. Fine? Converges pointwise. For each x you do it, it is bounded above by this. So it will converge to a supremum. Supremum will be for each x, consider this supremum. That will be a real number less than equal to 1. So it converges pointwise. But our domain was this. So I can apply Dini's theorem. Look, here is an application. Why I taught you Dini's theorem. By Dini's theorem, this converges to the function uniformly. Okay, right? And but the question is that converges uniformly, but why it has to be the limit? That means that's another trick. So that means Pn converges to phi uniformly by Dini's theorem. I have given the proof actually by Dini's theorem. But I want to prove that this. That exactly will establish my lemma. Okay, that's a simple calculation and that. Look, when you go for the limit, then Pn plus 1x, its limit n tends to infinity will be same as phi x equal to that. Exactly we have used it and we got phi x square is x. So that phi x equal to, anyway, phi is a non-negative function equal to root x. Okay, this is the thing we do it. Okay, that is the, so I have given the proof. Okay, so I have already said what algebra means and that. So next time I think I may take the class tomorrow. So because I want to finish that, I need to do some connectedness and some compactness is also left. So theorem 2.2, I want to prove. Now this, I will talk about the proof. I won't write everything in detail, but point is that now I think you should read the proof, okay, and see that it's very tedious, but it's not, idea is not now, is not difficult. So you should read the proof so that it becomes easier for you to understand what I talk about. Okay, so I am suggesting, and also I am suggesting that why you should read the proof. Read the proof carefully. And then you see that this proof, part of this proof, whether you can use that the wrong proof, theorem 11.3 of Alipranthes-Berkinson. You can prove it. Actually, it is inside the proof. I have used both supremum and infimum. Okay. Their mistake is that they are only using one and that. You can see that. That you have to do that. So I am asking you to read the proof carefully and see whether this proof from this proof you can get the idea to give a correct proof. Correct proof of this. You can give that. In fact, you will see that if you read the proof carefully, you'll see the lattice, so-called lattice version is already there. Eventually I am proving a lattice version of this, what they are called lattice version. I'm proving this. Okay, so that read the proof carefully. I will discuss the proof, how it is coming and that. Okay, very likely I will see you tomorrow. I will send a note, and otherwise I will meet you next Monday. Okay, I'll have to see that what jobs I have tomorrow at that. I think by night I will be able to tell you. Right now I'm not sending it. Okay. Okay, see you. Bye.